So I just want to get to know all of you. So uh, can like any like I want to know the background, what you are doing, so that I can get a good uh, estimate of what you all are doing, and accordingly, like it will be helpful for me to go through uh, these sessions. So, like, can anybody start like introducing themselves? Like, you can just turn on your mic and like say what you're doing, and you might be a UG student or a PhD student or a, PG student. We'll start with Sachin.
Hi, I'm Sachin, registered for PhD in NITK as external resistant. So this is for first semester course registered coursework. I've chosen as finite element method course.
Oh, nice. You are like in which department? Like, may I know?
Mechanical.
Like, mechanical. Okay. Good. Okay. Then you can have Anish. Uh,
Good evening, sir. Sir, I am
Good evening.
Anish Kumar, and I am working as a structural engineer. Currently,
Oh,
I am doing my part-time PhD at NIT Caricut. So, as for the coursework, I am taking this course.
oh, nice. Uh, Actually, I also have a civil engineering background. So I did civil engineering BTech, and then I did MTech in structural engineering, and then I went on to join applied mechanics department during my time.
Okay, sir. Nice to know that.
Next, we can have Ashwati. Ashwati Vinod.
Sir, I'm Ashwati Vinod. I'm a BTech student, Civil Engineering Department.
Oh, 1 second. Yeah. Uh, just a minute. I'll just take a call. Okay. Glad to know that BTech students are also part of this course. I hope like you will be able to uh, understand and uh, learn a lot from this course. This will be a good exposure. Uh, like because I didn't know, I knew finite element is a kind of a thing, but I didn't understand what it does during my BTech. Then we have Diksha Jain.
Hello, good evening, sir. I choose this course because currently I am doing PhD, part-time PhD from MNIT Bhopal. As my coursework, I choose select this course.
You are from, you are also in from mechanical department.
No, no, sir. I am from civil engineering department.
Oh, great. Uh, Next, Mahesh Dixit. Mahesh. Uh, we have also Manoj.
Hello, sir. I'm Manoj. I recently completed my MTech in Structural Engineering at NITK.
Oh, nice.
I
You are like,
enrolled this course.
yeah, yeah. Please.
Yes, sir. I enrolled this course to improve my knowledge in finite element method and structural dynamics because I feel I am a bit weak in that part.
Ah,
That's
nice. Mahesh
Hello.
was, yeah, yeah,
Yes,
Mahesh.
yes. Yeah, yeah. Very good evening. Myself, Mahesh
Hi.
Dikshit. I am doing PG in structural engineering. I'm basically civil engineer. I
Ah,
have completed B, and then recently I completed my second semester of structural engineering PG
oh, great.
under Mumbai University. I am from Navi Mumbai. I'm
Oh,
doing it
nice.
from Pillai College of Engineering, Navi Mumbai.
Okay,
So
okay.
that's why I joined this course.
Yeah, hope it helps you.
Yeah, yeah.
Uh,
Okay.
Next we have Sona.
Hello, good evening, sir. My name is Sona Vibhas. I'm currently doing my BTech in civil engineering. I'm joining the course as part of my honors degree.
Ah, okay. You are in which year of your BTech?
Final year.
Okay, okay, great, great. Next we have Sulaikha.
Good evening, sir. Myself, Suleika Kasim. I am doing 7th semester BTech degree in civil engineering.
Oh, great, great. We missed out, I think, Amrita.
Hello, good evening to all. I am Amrita S. Krishnan. I am currently doing my BTech course in civil engineering, and I joined this group as a honors degree.
Okay. You are in which year? Final year?
Yes, sir.
Okay, okay. Great to know. So, this is a very unique course because, like most of the times, whenever you learn finite element, you won't come across the combination, this kind of combination, like along with structural dynamics. So, like finite element method or finite element analysis, this is taught separately as a course, and then we have structural dynamics or computational structural dynamics, or you can say different kinds of names like mechanical vibrations. So that is taught as a separate course. But whenever we do any kind of analysis like dynamic analysis, we use FEM along with structural dynamics. So that's why it is a course which will give you the best of both worlds. Like you can learn finite element and then you can apply it for dynamical systems. Like let's say if you are a civil engineer, so if there is a building which is undergoing uh, uh, which is subjected to earthquake motion. So it is not like a static load. So it will be a dynamic load. So load will depend on time. So then you can use your building model with finite element and computational structural dynamics to analyze it. And like similarly, if you are a mechanical engineer, you have aerospace structures or any kind of machines. So they undergo while in operation, they undergo large amount of vibrations. And like if you want to analyze them, it's like you should make a finite element model of that, and then you should analyze it for the loads which are being applied due to uh, due to the operation. Like it might like they might be time dependent loads, so if the loads are time dependent, like if the load is changing with respect to time, then we should use structural dynamics. So that's why like any kind of structure subjected to any kind of load, we can use this. We can use these concepts and we can analyze and we can determine uh, how much amount of uh, stresses are being developed, how much amount of deformation is being developed, and is it permissible or is it not permissible that the machine or the structure goes through this amount of vibration or like deformation or something else. So we can analyze and we can keep in check in designing while designing, and also uh, like nowadays we also have digital twins like which exactly replicate the structure's behavior on a computer. Like you make a computer model of the structure, like you have abacus or different kind of uh, modeling softwares. You make the exact replica of the building, and you place sensors on the buildings, and you track the measurements, and based on the measurements you try to run analysis in your computer and replicate the exact behavior of the building which is present in the field, and you try to find out where are the maximum stresses occurring on the structure, and if there are any damages happening, if there are any damages in the structure, or is it near to failure, and like if it is near to failure we can stop the operation and we can go for maintenance. We can plan the uh, maintenance strategies according to that. So it's it's a very helpful thing. So finite element method is like a numerical technique. So basically we are like solving uh, whenever we model structure. So we are going to use governing equations. So governing equations are nothing but the equations of motion. Or let's say if you have something, if you have a static system, like we know that using the Newton second law, we can uh, get this equation of uh, force balance equation. So this is a equation, and this you can also write it as uh, force. You can also write as ma into kx. K is the stiffness of the spring. Then a you can write as d square dx square by dt square, which is the acceleration. So x is nothing but the displacement of the spring. So if you differentiate it two times, that is acceleration. So this is a differential equation. So similarly, going forward, like when we go into the course, we get lot of like we do this mathematical modeling. So mathematical modeling is nothing but you have a structure, you want to analyze it. If you want to analyze it, you have to do some kind of mathematical modeling. Like you should make a mathematical model. So mathematical model, you can use this kind of laws, like law of conservation of mass, law of conservation of energy, or law of conservation of momentum. So this is law of conservation of momentum. So you use this laws and you can get a mathematical model of the structure. So in second week, we are going to start mathematical modeling, and then we will get the equation of motion of the structure. So for a simple spring, this is the equation of equation of the uh, like a spring balance, spring mass balance. If you have, this is the equation of motion, you can say like that. So if it is going some kind of deformation, this is the equation of motion. So uh, in order to solve these differential equations, like let's say if I have this equation of motion m into x d square by dx minus kx is equals to 0. So this is the equation of motion. Now I want to solve it. Let's say you are giving some initial velocity, initial displacement, like you just displace by the spring by uh, some distance. Let's say this is x naught, and if you leave this spring now, it will oscillate. So it will have a to and fro motion. So at time t is equals to 0, this is the displacement, and let's say you also have velocity, which is like, let's say you are giving initial velocity is 0. So when I'm writing dot, it is nothing but x dot is equals to dx by dt. So I can also write d square x by dt square as x double dot. Okay. So I can replace this with x double dot minus kx is equals to 0. So if I want to get x at, let's say, some point t is equals to 2 seconds, I want to determine what is the location of the body at t is equals to 2 seconds. So for that, I have to solve this equation of motion, right? Like I have to integrate this. So I have to integrate this, like if I, let's say, integrate this with respect to time 2 times, I'll get the solution. So that's what is called solving of the equation of motion to get the solution. This solution, like this integration, we can do it in a very numerical way using the finite element method. Like if you want to do integrations in computer, like let's say there are a lot of complex integrations, complex functions which will arise. So we cannot do integration, or computers cannot do integrations of these complex functions, and it will be very computationally difficult task to do, and like it will also like sometimes take a lot of time. So uh, instead of doing the integration analytically, like we can also do it in a numerical way. So one kind of like using the numerical integration, like we have a technique called Gauss quadrature, like we will see it. So using these kind of techniques, all these techniques, we came like academicians came to a simplistic method called finite method. So which will solve this governing equation of motion in a numerical way. So when I say numerical, so numerical, you might have gone through this numerical methods courses in your I think maybe third or fourth semester or second semester of undergraduation. Like instead of, let's say, you have some uh, start up with. Let's say you have this kind of function. Uh, you can, let's say, sin x function is there. Like this is x and this is y. So this is sin of x, and let's say this is 0 to 5. And if I want to do the integration, so what I can do is I can take integration of 0 to if I want to find out the area between the area in this curve, area enclosed by this curve, I can use this and do it. Like so, we know that integration of this is minus cos x, and I can take from 0 to 5. Okay. So this is a analytical way of doing. So analytical way is like we know the integration of sin x is minus cos x, and we will substitute this values 0 and 5 for to get the different integral of this. Okay, but there are a lot of functions for which, like let's say you don't know this sin x, like let's say you get some kind of very random curve, like by doing experiments or something. Let's say you get a random curve and you don't know the form, or let's say if the function is like very complex, some sin x into cos x, uh, uh, and then x cube, something like this, like a very complex. function is there. There are a lot of functions for which analytical integration doesn't exist. Like you cannot do integration. Like you cannot get a formula like this. Like integration of sin x is equals to minus cos x. You won't get a formula like this. For those kind of functions, we can use numerical techniques. Like we have the Simpson's rule or the rectangular or the trapezoidal rule or rectangular rule. So what we do is like we make these small rectangles like this. Let's say this function is f of x, and this is x1, x2, x3 like this. Let's say you take n plus 1 points. So you can take area of each of this rectangle and you can sum all the areas. Let's say this width of this rectangle is hi, let's say hi into, let's say, this you take some value which is some xi by 2, something like. So you can sum this from I to n plus 1. So this is a numerical way of doing the integration of complex function. Of course, this is like not exact. You won't get a closed form answer like this. Closed form means like you will get an expression like this. For integration of sin x, you will get a closed form uh, solution which is minus cos x. But for these complex functions, you have to do some kind of numerical use some kind of numerical technique. But when you integrate this, like when you approximate these areas as rectangles, you are leaving out some kind of errors. Like you are leaving out some kind of errors. So there will be lot of like small errors we will get. Like the integration which we'll get using this numerical techniques is not exact, but it is approximate. So we can make it like we can take like we can get the integration solution very close to the true solution, but it will not be equal to the true solution. So this is called approximation. So numerical techniques are always approximate. So this is a compromise which we have to make in order to get the solution. Obviously, it works for us. Like we can make some kind of approximation. We can give some kind of leeway, and we can accept some amount of errors. So that will not be a major issue, and we will be happy with it. If there is a small error in my solution, I can be happy. Like I'm getting the solution. Okay. So there is no way to get it. If I'm getting it in a fast manner, like using the computer, you can do this computations in a very like in a matter of 1 second or a split second, you will get the solution. So we will accept this kind of approximations. Okay. So, but there is always a uh, danger of this precisions. Like let's say we have seen this example in the course. So when we take when we have, let's say, uh, when we have a number, let's say 2, and if you if you take the square root of 2, and then if you take the square root of 1.414, so when you take the square root of 2, you will get some kind of 1.414, some like beyond these values goes, but we are like just rounding off here. So obviously, like computers cannot store infinite number of decimals. There will be a limit to how much it can store. So depending upon the computer, uh, depending upon the bits, like we discuss what is it. So it can store up to only certain amount of decimal values. So that's why we round it off and we take some uh, and remove these decimal points. So if you square it again, if you take the square root again, and if you square it, you should get 2, right? But you will get some kind of let's like only like you see, if you square it, you are getting 1.999. So if you square it and if you again square it two times, you will get 1.999. So similarly, if you go on do if you go on to do this, like at the end, like taking square root multiple number of times, you will get one at the end, but near to one. So, but if you take the square, you won't get the exact value because like you are rounding off. So this error happens due to rounding off because we are only taking here four significant digits. So one is before the decimal and three are after the decimal point. So this loss of accuracy due to the finite precision is is something which we have to be very careful about when dealing with computers. So if we don't have this knowledge, we might end up getting like unknowingly you will get like you will run the program, like you will write some code to do the finite element analysis, and like if you don't know this, like if you don't take care of this, you will get some kind of abrupt solution which is not near to the exact solution. Like this, here we are getting 2, here we should get 2, but we are getting 2.782. So this is not acceptable. So where is 2 and where is 2.782? Like it's like 0.782 error is there. So that is the thing we should be careful about. So uh, this man who is in the picture, he is uh, John von Neumann. So he is like uh, uh, one of the greatest mathematicians or a physicist. So um, he was working with uh, all these people like during this nuclear uh, nuclear war which was going on. Like if you know about the history of the world, like after like before World War, they had to make an atomic bomb. Like if you have seen this movie Oppenheimer, so like America wanted to uh, make a nuclear bomb or an atomic bomb. So uh, so they like invited like all the best scientists in America and all their allies, and they made a laboratory called the Los Alamos National Laboratory, so which is in the southern part of USA in New Mexico region. So these people like during that time they did lot of discoveries so to make this atom bomb or nuclear bomb. So like along with John Newman, Oppenheimer, there was Richard Feynman, and like a lot of people, lot of scientists like Albert Einstein. So you can name lot of people who have worked on that project. So during that project, like lot of things came out. Like many people contributed in different ways. So John Newman was like one of the guy. Uh, Once again, yes. Just give me a second. So, so von Neumann was one of the scientists or the mathematicians who was responsible for this framework, which architecture of the modern computer. So, like earlier computers had different architectures, like different than this. Like we have a central processing unit CPU. Uh, like most of the model computers have like this. Like we have a main memory, secondary memory. So main memory is like the random access memory. So there are registers. Registers you can say as cache, which is present in the computer. So input devices, output devices, and there is a bus or connection which is going and connecting all these units. So this was proposed by him. So why do computers have uh, this uh, this precision limit is like computers uh, have this transistors. So transistors either you can have low, like transistors are like the electronic switch. These are kind of electronic switches. Like they can be either on or either off. So like you arrange these transistors uh, in a group. Let's say like in a group, and you can name this each of the transistor as a bit. Okay, and there are like if you have 8 bits, then you call it a byte. So there are different terms, but so whenever we work with computers, so like uh, uh, like we give a lot of numbers, or let's say you type words in Notepad or Word. So what happens is like all these things get stored as either zeros or ones. So computers, like whatever we write in the computer or give instructions, everything goes and becomes zeros and ones. So everything goes and makes the transistor turn on or off. So if it is off, then it is zero, and if it is on, then it is one. So computers know this only binary system. So we have like as humans, we use the decimal system. So we know that during like from the uh, start of the civilization, like I'm not sure about this, because like we had 10 fingers, so we counted in the basis of 10. So we started with uh, let's say 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So then like 10 fingers are completed, and then you after that what you do, you again start with 0, but this time in before 0 we keep 1, and then we like keep on doing this, and then you get then you go till 19, and then you go keep it, then you keep you will get 0, and then you keep 2 here. So like that we do in the uh, decimal system. But in the binary system, we have only 2 digits. Okay, either it is 0 or either it is 1. So we start with 0. So let's say if you want to count, so if you want to count, let's say number of apples. So if you have 0 apples, you will just write it as 0. And let's say if you have 1 apple, you will write it as 1. Then after that, in binary system, you again go back to 0. Okay. Now before 0, you keep 1. So this is 2 in binary system. This is binary, and this is decimal. Okay. And then you keep 1, 1. And this is 3, 1, 1. In binary system is 3 in the decimal system. Now again you go back to 0. Now we have to uh, take two zeros and we have to keep 1 before here. So like this, uh, counting goes on in the binary system. So whenever you type 4, you will be whenever you type 4 in the computer, this will be stored as 100. So let's say if you have like 8 bits which are storing this, then it will store it as 000 and 0100. So it will be stored like this. So 4 will be stored like this in the computer. So this is how computers store this information or like do the operations. So they have only this binary system which they can use because of this transistors which we have. So I think in coming few years we are going to see a new revolution, like quantum computers are going to be a thing. So where you can have you can store some other number, like in between 0 you can store some 0.1, 0.2, 0.3. That is also possible because of the quantum computer. So that is a major field of research or development which is going on. Like you might see in a few years, uh, we will get those kind of computers too. But at present, like whatever the computers which we have are uh, these computers which, and the chips uses transistors, and they use this bits. Okay, so the binary system. So bit is nothing but binary transistor. Uh, I think uh, the full form, like why, how does the name uh, bit came? Yeah, bit means binary digit. So binary digit, bit. Yes, binary. So let's say you have 3 bits and you want to uh, in this example we have 3 bits and we want to do the counting or store some number. So let's say you have only unsigned decimal. So then you start with 0, 1, 2, 3, 4, 5, 6, and 7. So we go like this. So 0, 1, 1 is 2 is represented by this, 3 is represented by this, 4, 5, and 6, and 7. Like this. Then if we have if you want to, let's say, also have negative and positive integers or negative and positive decimals, so you can use the sign and modulus convention also. So when I say convention, so convention is something we decide the rules and we follow all the rules. Let's say uh, like in India we have the rule that we should drive on the left side of the road. So that is a convention which has been going on from a long time, and we do it because we have, like, in order to maintain the order on the road and avoid accidents, avoid congestion. So we follow that rule. So that's why, like, you can use like different uh, conventions. So one kind of convention is the sign and modulus, the other is two's complement, and the other is excess uh, minus k. So like here in this the first zero represents the sign. Okay, so the first zero represents the sign. So first bit represents the sign. So the if the sign is positive, then we keep the first bit as 0. And if the sign becomes negative, then we keep the first bit as 1. Okay, first bit as 1. And the remaining things denote the value of the number. So 0, 0, 0, 1, 1, 0, and 1, 1. So these things denote 0, 0, 0, 1, 1, 0, and 1, 1. These things denote the count. Okay. So you can also use that 2's complement and XSK, which is the shifting of the axis. So different kind of convention we can use and do our uh, calculation, do our calculation and the store the. So all the integers which we have can be uh, uh, used for like various kinds of operations like additions. So additions are nothing but subtractions are nothing but addition of a negative integer, and multiplication uh, can also be done as repeated addition, and division is nothing but repeated subtraction. So similar like whenever you have some integers like you can add it you can add two integers and you can get the exact answer of the addition as long as the computer can accommodate the assigned bit width. Okay, let's say if you have a calculator and like you are adding some number like 99999999999, like it can only store like I think 7 to 8 values, or like 14 to 16 values. If you take values more than that, it cannot store it. So if you do the addition of those kind of numbers, obviously there will be an error. The addition won't be exact. So that is the thing which we have to take care. Like uh, that is called overflow of carry bit. So like you have let's say your computer only has 3 bits. So let's see how we do addition in binary system. Okay, you have 1 0 0 0 1 1 and 1 1 0. So 1 plus 0 is nothing. 1 plus 0 is 1, right? So I'll just write 1. So 1 plus 1 is 2. 2 is nothing but 1 and 0, right? 2 is nothing but 1 and 0. So we have a carry here. So we have a carry. So 2 is nothing but 10 in binary system. Remember, 2 is nothing but 1 0 in binary system. So there will be a carry. So now I will write this. And then again 0 plus 1 is nothing but 2. Again this will be 1 0. So it will be 1 0. So but our computer only has 3 bits. Okay, 3 bits. There is no space to store this. So if you do this addition and you get this answer 0 0 1, which is like your answer is 1, but it is not actually, it is something else. So 0 1 1 is nothing but 3, and 1 1 0 is 6, right? So 3 plus 6 is 9, but you will get the answer as 1. So because of the limitation that computer has, so it cannot store this in the memory, and we will get a wrong answer. So that's what there is no space to carry this bit. So that's why we will get a uh, wrong answer. So that's why like we go to so whenever we have large numbers, so what we do is like gravitational constant or like very small numbers, we use this floating point representation. So let's say if we have something like some very huge number, uh, 6.023 into some 10 to the power of 27. So obviously, like computer or calculator cannot store uh, like if I don't use this kind of representation, I cannot store this number. Like you cannot store uh, 34 digits or 35 digits lot of times. You cannot store this if your computer has uh, lesser number of bits, you cannot store this number. So that's why you can uh, still make use still store the large numbers by using this floating point representations. So what happened is there were a lot of discussions during I think during this nuclear war or the Cold War times itself. So then people came up with this standard, which is the IEEE 745 floating point representation. So obviously, so computer will store everything as 0 and 1. So like so this is the so if you have any large number or if you have any small number, so computer will store uh, as this. So based on the single precision or the double precision format. So single precision means whatever the computer which you have, it can store 32 bits. So it has 32 bits. Uh, Double precision means it has 54 bits. So here you can see this is an implicit thing. Like implicit means this is an understood thing. So I don't need to store this -1. So I can store yes. So if yes is 0, the number is positive, and if yes is 1, the number is negative. Whatever the big number or the small number which you are storing. So uh, you can store in the first bit. First bit stores the first bit contains the uh, information about uh, information about the sign of the floating point number. Then this E, which has 8 bits, like you can store 8 bits here, like that we can approximate like that we can store like here we have because computers use the binary system, we are using 2 to the power e here. Okay, so whatever you get here like 2 to the power 1 2 3 4 something like whatever you get here, that will be stored as e here in this 11 bits or here in single precision 8 bits. Then after that, you will write the number as 1 point something like this. So in computer, like you will have something like this 1 point f and 2 to the power e. So it can be a negative, like whatever the big number you get, you will convert like this and you will store it like this. Only ones and zeros are possible. So this 2 is understood. So we won't store. So E and this F values and this S value we will store. So based on this, we will write like computer has some kind of program running it behind. So if it is a floating point, it will store this value, this values and this value and uh, do the operations or save it in the memory or do something like that. So this was a standard which was followed and it has been used since then, like to avoid confusions. So this is just a uh, convention kind of thing, like it has been going on, like some standard has been set and it has been going on. Okay, so now we will see some problem on this. Let's say if you have, let's say, 32-bit wide data, 32 bits, like let's say you have computer with 32 bits, 1, 2, 3, something like this. There are 32 bits. So you have this much amount of space and you can fill it with zeros and ones. Okay. You can fill it with zeros and ones. So uh, what is the largest unsigned integer? So there are no signs. Positive and negative is not there. We are just uh, storing unsigned integers. Okay. So unsigned integer number that can be represented on this 32-bit wide data unit. So what is the largest number which you can store in this? So anybody has any idea like how we can answer this question? You can just like whatever you have, you can tell me. So it's not that uh, you will be judged or something. We are just trying to learn. We can have very fruitful learning if all can participate. Okay. Anybody? Okay. Okay. What we can do is, so if let's say, if I have all the bits, so if I have, let's say, all the bits are stored with 0. So all the bits are stored with 0. Then what is the number which we are storing in this? Can anybody answer? Okay. So if all the bits are 0, then the number which we are storing is also 0. Okay. And let's say if the last digit is 1, if the last digit is 1, then what are we storing? You can also type in the chat uh, if you are like not able to answer in the mind. So if the last digit is 1, we are just storing 1 here. Okay. If if the last digit is 0, but the last but one digit is 1, what are we storing? Like you have 0, 0, 0.
Two,
Yeah,
sir.
2. Yeah, very good. If the last two digits are 1, then what are we storing?
Three.
Yeah, 3. Very good. So it's like that. So the more number of ones you have, it means you are storing the largest number. So if I store all the bits with ones, like I have 32 bits, and if I store all the 32 bits with 1, what is the largest number which I can store in this? Anybody has idea? Any idea? Okay. So yeah. Anybody answer? Uh,
Sir, is it
Anish.
all digits are one?
Yeah, all digits are 1. All digits are 1. All bits are 1. 32 bits. We have 32 bits in which we can store the data, and all the bits are filled with 1. What is the largest unsigned integer that can be represented on this 32-bit wide pattern? Any idea? Any- Okay, let's see. Let's say we will take a simple example. Okay. Uh, let's say we have only 3 bits. Have only 3 bits, and each bit is filled with zeros. If let's say if I have 3 1 like this, largest so here this is 2 power 0, here this is 2 power 1, and here this is 2 square. Okay. One, two, four. No, this is 2 power 1, and this is 2 square, and this is 3 square. Okay. So as we increase the number of digits, we are increasing the number that we can store by multiples of so uh, or powers in powers of 2, because this is the binary system. So we are increasing the amount of the largest number which we can store by largest number which we can store in powers of 2. So if we have 3 bits, so we can store 2 cube minus 1. So minus 1 is because we are starting the counting from 0, right? So that's why I'm removing minus 1 here. So I can store, if I have 3 bits, I can store maximum number which I can store is 8 minus 1, which is 7. So that's what we saw here. So the maximum unsigned integer which we can store using 3 bits is 7. So if it goes beyond this, we cannot store it, obviously, because 8 will be 100. It will be 1000 like this. So we cannot store beyond this. So if we have 3 bits. So let's say if you have n bits, the maximum number which you can store is 2 to the power n minus 1. So this is the simple formula which you can remember. Okay. So this is the maximum which you can store. So minimum can be like all the bits are 0, then that is the minimum. So you can store 0. So 0 is obviously like we don't need three uh, bits to store 0. But if we have 3 bits, the maximum which we can store is 7. So beyond 7, we cannot store. So if I have 32 bits, if I have 32 bits, the maximum number which I can store is 2 to the power of 32 minus 1. So this minus 1 I am taking out because I am starting the counting from 0, right? So we are not starting it from 1. So we are starting from 0. So 2 to the power of 32, if you do it, you will get this value 4 to 9 4 9 6 7 2 9 5 9 6, I think. Minus 1, you will get some value, you get 4 to 9 4 967295. So this is the largest number which we can store, which we can store if you have 32-bit wide data. So like there are computers, like whenever if you are using a computer, obviously like the modern day computers, they have 64-bit precision. So like all the transistors are placed in a group of 64 bits. 64 transistors will be placed side by side. So obviously it can store the maximum number which the largest number it can store is 2 to the power of 64 minus 1. Okay. So if it goes beyond this, it cannot store. So then you have to go and use this kind of representation, floating point representation, or do some kind of thing so that you can store large numbers. Okay. So this is the thing you should remember, 2 to the power n minus 1. Okay. Next, let's say if you have if you have to do some computation, you have to do some computation which is 4.3 into 10 to the power 18 and 1.6 into 10 to the power of 17 and 5.2 into 10 to the power of 12 plus 1.2, 3.8 and 2.8. Okay. So these things might be very like boring, like we have not got into the subject yet, finite element. These are just the numerical things which we are learning, but these are like very important things uh, because whenever we do some kind of calculation or coding using a computer, we might not be knowing what is going on inside. So this is just trying to make you understand what is going on inside the computer so that we might be aware if there are inaccuracies occurring in your solution. You should be aware like what might be happening and what will be the reason, and you should be aware what you can do to avoid that. Okay, let's say if you have this ca- following computation, what will be the issue in this? So let's say if your computer can only store one decimal after the after 1 digit after the decimal, and it can only store let's say this. Okay, uh, two decimals, two digits on the power of 10. Like this, this is the limitation which you have, and like data is stored like this, and you are summing it. You are summing this large number with a very small number. So what will be the issue with this? So I will give you four scenarios. So you should tell me like which what is the problem here. One is the exponent is very big, and two is addition is beyond the floating point precision. Addition is beyond the floating point precision. And three is operation will result in an overflow. Overflow is something which we have seen, right? Like because there is limitation of bits, we cannot store this one like we have seen here. Like we cannot store. So that is the problem of overflow. So operation will result in overflow. And there is no issue in this. Like computer can perform this and give you a solution. No issue at all. So what do you think is the correct answer for this? Anybody has any idea can share. Anybody? Okay. So what is the issue with this is, so when you have this big number 4.3 into 10 to the power of 18, and if you are adding this small number 1.2 to it, after doing this addition, computer will give you a result of 4.3 into 10 to the power of 18 only. It will not give it will not give 4.33 something something, like you have lot of zeros uh, up to like four. This you can write as 43,000 something, like lot of zeros, and in the end there will be 1.2, like this is a very large number. So obviously it cannot be stored, like you cannot store this big number in the computer. So that's why computer use, like we are using the floating point representation. So after doing the addition, computer will remove all this, like computer will not consider this, and we will do some kind of round off, and we will only store zero point 0.3 into 10 to the power of 18. Similarly, if you do this addition, computer will store this as 1.6 into 10 to the power of 17 only. So it will not store it as 16 160000000 in the end 3.8. No, it will not store it like that, because it doesn't have the capacity, and like we are using the floating point representation. So when you do this kind of calculations, when you are like adding a big number with a small number, so this kind of thing happens. So we have to be careful about that. So this uh, this is the answer for this, which is addition is beyond the floating point precision. So like after 3, whatever, if you add like point after point 3, whatever comes, it will be removed, and like we are doing the round off, so it cannot be uh, whatever the answer which we get is not the exact answer. So like we will get the same answer. So that's what happens. Like this addition is beyond the floating point precision. Okay. Let's say if you are like doing this addition of some addition like 4.3 into 10 to the power of 18 plus 0.2 into 10 to the power of 18, this will go here. So this will be added, and you will get a 4.5 into 10 to the power of 18. So here there will be a no issue, because we are adding two large numbers. So computer will give this answer. But when you add a small number, which is a very big number, so limit of floating point precision uh, will challenge the computer, and it cannot give you it cannot store the correct answer for that. So this is something which uh, we have seen in the course, and we can call it uh, uh, catastrophic cancellation of significant digits. So because after, like we have significant digit only one, that is the capacity of the computer, which or the computer, or like the program which we are writing, we can only store one significant digit after the decimal. So uh, whatever after 3, whatever the things which are there, they will be removed, and this if we do the addition, we will get this problem of catastrophic cancellation. So this is called careless numerical uh, errors, which can happen. So we have to be careful about these kind of things. So That is one kind of problem which we will experience. Okay. So then we went and saw like after this discussion about the precision and bits, storage of a computer and binary system architecture, approximations, discussion of approximation. So we had this discussion about the vector spaces. So any point like in the space can be represented as a vector. Like if you have a three-dimensional space, uh, x, y, z, and if you have a point, let's say I call it the xyz, I can store it as a vector. So I can represent it as like this, or I can also represent it as xi plus yj plus zk. And here I cap, j cap, and k cap are the unit vectors, orthonormal unit vectors. So these are also called as the basis vectors. So basis vectors are something, if I use these three basis vectors, I can span the entire space. So if I have three basis vectors for a three-dimensional space, I, j, k. So one is 100, the other is 010, and the other is 001. So if I have these three vectors, I can represent any point on the three-dimensional space using these three vectors. Whatever may be the vector, whatever may be the point, or whatever may be the vector, I can represent that vector or a point as a linear combination of these three vectors. So if you take this, you can just simply write it as uh, x into 100 plus y into 010 plus z into 001. You will get nothing but x, y, z. So these are called basis vectors, and these are like finite basis. Like we have three bases here for a three-dimensional space system. We have three bases. So basis is nothing but something which we can use to span the entire space. So if you have, like, you can, instead of this, you choose some other basis also, some other three vectors also as a basis. Uh, the only thing is that they should be independent, linearly independent. Like you cannot choose vectors which are linearly dependent on each other. Like let's say if you have uh, if you s- if you take 001 100 and uh, 010, and you cannot take another vector as, let's say, uh, 1 1. So you cannot choose this as basis, because if you sum these two, you will get this vector. So this is not a correct basis. So this should not be possible. Okay, that is the criteria which should be taken care. So basis vectors should be independent of each other. Yeah. So this is like this is the discussion about vectors. So we can also have uh, uh, like basis, all like whatever the basis which we can store the basis. We can also represent it as a matrix, like 100, 010, and 001. So like we can also use this kind of representation for the basis vector. So because this is a three-dimensional space, we will have three basis vector. So if it is an n-dimensional space, you will have n basis vectors. So this matrix size will become n cross n. So if you can also have infinite dimensional space, like these are the things, like beyond three dimension, we cannot plot it, like we cannot represent it on the paper, and we cannot imagine that. So, but they are also some kind, they also exist. Like we can do those kind of calculations too. So vector calculations can be done uh, lot of like we will see in the course, like we have lot of uses of vectors. So like we will get a lot of matrices, and like when you get a column vector you can also call it as column, or let's say you if you have a column matrix, okay, column matrix or a row matrix. When I say column matrix, it has only one column, and when I say row matrix, it has only one row. This can be these matrices can be called as vectors. Okay, so you can represent it these matrices. You can represent these matrices as vectors. Okay, so don't confuse like vector is some kind of different thing, or matrix is so column matrix is a different thing. Like column matrix and row matrix, we can like we will call these as vectors only. So if you have a column matrix or if you have a row matrix, we can call it as a column vector or a row vector, something like that. So you should get used to this kind of notation, because like a lot of people are there who are they're BTech. So I'm just clearing that. So I didn't knew this. So when I was uh, in a bachelor's, so later when I did my MTech, I got to know these things. So I'm just letting you know. Okay, and well, let's let's solve a simple problem. Let's say if you have a vector, okay, you have a vector. Uh, I will call it as vector, okay. I have a vector which is -2, 4, 1, or you can also represent it as minus 2.2i plus 4j plus k, or 1k, like this also. You can do. And you have another vector uh, b, which is 1 minus 1, and or you can also write it as 1i plus 1i minus 1i minus j, and 0k. So no need of writing this. You can write it as 1i minus. Okay. So I want to project this vector onto. Uh, I want to project a vector onto the b vector. Okay. What is projection? Projection is nothing but let's say if you have some. I'll just show in a 2D. If you have, let's say, in a two-dimensional system, two-dimensional space, you have some kind of vector, let's say. This is the vector which is like passing through the origin, and you have position vector, some kind of position vector. If you want the projection of this vector on the x-axis, so you will draw a straight line. You will draw a straight line from this point, which is parallel to the y-axis, and it will cut the x-axis at some point. And whatever you get, this is the projection of this vector on the x-axis. Here, if I want the projection of this vector on the y-axis, whatever I get here, this vector is nothing but the projection of my vector on the y-axis. Okay. let's say my vector is x, like this point is x comma y. I can write this vector as xi plus yj. So if I want to project this vector onto the y-axis, onto the x-axis, so you know that this point will be x comma 0. Okay, this point is x comma 0. So the projection of the vector is x I cap. Or instead of this, I can also do this dot product of xi plus yj and my unit, this x-axis, what is the basis vector, what is the unit vector of the x-axis, which is I cap, just I cap. So j and k have 0 coefficients, right, like this. So this is for unit vector for x-axis. So if I do this also, so I dot you will get 1, and remaining things, like if you do the dot product of j dot and k cap, so because these two are perpendicular, so dot product of perpendicular vectors is 0. So you will just get, this is the projection. Okay, so this is the projection of this vector onto this. So you can do it like that. So you can, this is another, this is one way of doing it. And another way of doing it is, whatever the vector which you want to, whatever the vector which you have, you can write it as a column vector like this. And whatever, like I want to project it, let's say I want to now this time I want to project it on y-axis. So I will write it as uh, a column vector. So I want to get the projection of this vector on the y-axis, right? So what I'll do is I'll take the transpose of this vector xy and I'll multiply with this. Now what I'll get this as the value. So value, the projection of this vector, onto the y-axis is y. So this is the way of getting the projection. You do the transpose of the vector which you want to project, and multiply it with the vector on which you will project. Okay, so that's how we do the projections. So here I will do A transpose into B. So I will have -2, 4, 1, and I will have 1, -1, and 0. So if you multiply these two, you will get a -2 and -4 plus 0. You will get the answer as -6. So this is the projection of this vector. This is, let's say, I will just take another paper. So take another paper, and what was that? 2 -2, 4 and 1. Let's say this is x, y, and z. So this will be somewhere. Okay, so 2, these are positive. Okay, these are, let's say, and let's say this is negative z. This will be somewhere inside. Okay, -2, 4, and 1. No, here itself. -2, 4, 1. So this is my vector, and I want to project it on 1, -1, and 0. So 1, -1, and 0 will be, and it will be here on this. This will be 1, -1, and this will be here. Okay. So you want to project this vector onto this, like three-dimensionally. It is like difficult to explain, but let's say you have two vectors like this A bar and B bar, and you want to project this vector onto this vector. Okay, this is the some kind of angle between them. So you want to project this vector onto this vector, you do the dot product and you will get the projection of A on B. Okay, that's how we do the projections. So you just projection of vectors, you just take the transpose and multiply it with multiply it with the vector on which you want to project. Well, let's now I have a question. Like you in Euclidean space, Euclidean space is nothing but the Cartesian space which we use. In Euclidean space of n dimensions. Like instead of 3 dimensions or 2 dimensions, let's say you have n dimensions, which we cannot draw on the paper or we cannot imagine. Any arbitrary vector x can be represented as x is equals to sigma 1 n xi ei. Okay, so like you have, if you have let's say 2 dimensional vector, you can write it as x1 plus x2 e2. So this is nothing but x1 comma x2. So e1 and e2 are the basis vectors. So if you have a 3 dimensional vector, you can write it as x2 e2 plus x3 e3. So whatever we wrote, like we did. So e1 e2 e3 you can call, like in 3 dimensions we call it as I cap, j cap and k cap. So here we are calling it because I want to write in this form, I'm just writing it as e1 e2 and e3. So if you have this kind of representation, like if you have a vector like this, where ei are the ortho normal base vectors, basis vectors. Okay, base vectors, and we know that xi's are the projections, right? Xi's are the projection of this vector. Like let's say here we have seen, right? So xy, if you have coordinates xy, x is nothing but the projection of uh, the vector on the x-axis, and y is nothing but the projection of vector on the y-axis. Projections on this vector. So the question is, are this are ei unique? Are ei unique for given vector? For given vector. So if I have any vector x, so I can represent it as a linear combination of basis vectors like this. So the question is, are these basis vectors unique? Like, should I use only E1, E2, E3 or I cap, J cap as the basis vectors? Or there can be other basis vectors which I can use to represent a vector? So that is the question. So do you think we only have I cap, J cap, K cap? We can only use I cap, J cap and K cap as basis and represent the vector, or we can use another kind of basis vector to represent this vector x. So what do you think? What might be the answer? Is this unique? Are these basis vectors unique, or like no? We can use another set of basis vectors also uh, to represent this vector. Anyone? Sachin or Rashidhar? Can you hear? Yeah, yeah. Yes, please, Shashidhar, you were speaking. Uh,
I think it will be unique.
no, you can. It is not unique. You can like have infinite set of basis vectors. I'll explain how. So let's say you have a two-dimensional vector, two-dimensional space. So I'm using this frame of reference, X, right? And there is a vector, okay? There is a vector there is a point in the space, X, right? And I will represent this as a position vector, okay? So in a two-dimensional space, I need two basis vectors to span the entire space, like it span the entire two-dimensional space. Like in this space, like in this two-dimensional space, I can use these two basis vectors I cap and j cap and represent any vector. Okay. So the thing is, instead of choosing this I cap and j cap, like I can use also another frame of reference. Instead of this, I can also use like some rotated frame of reference like this. Let's call it uh, what we say u and v. U and v. Let's say the point remains same. Like I'm just rotating the axis. I'm just rotating the axis. The point xy will remain same, but I'm just rotating the axis. So this is like change of perspective. So somebody is seeing a body like this, and somebody is like seeing the body in a like tilted position. So, but the point will remain in the space at the same position, but the way of looking at that point is different. So, like now you can use this u cap and let's say v cap as basis vectors. Okay, so obviously you can see that these two are perpendicular and these two are independent. Like one cannot be represented as a linear combination of the other. So we can use this, also use this u cap and v cap as the basis vector. Like similarly, instead of this, like you can also have a you cannot like let's say like you can tilt it even more. Like this is your point. You can tilt even more like this. So we can have infinite number of basis vectors as long as they are independent. Uh, we can use these basis vectors to represent uh, any point on the space. So this is not unique. So I hope you understood. Does anybody have any doubt in this? Anybody have any confusion? Shashidhar, did you understand?
Oh, yeah, I understood.
Yeah. Okay. Thank you. And okay. So next thing we will see is we will see what is like Gram-Schmidt orthonormalization. I think there are some questions on Gram-Schmidt orthonormalization uh, in the assignment this week. So we have a vector, let's say 1, 2, minus 2, 3, 1, 8, and minus 3, 4, and this. So Gram-Schmidt, what does Gram-Schmidt organization does is, so you have these three vectors. So these three vectors, column vectors are there. So these three column vectors are there: 1, 2, minus 2, 3, 1, minus 8, minus 4, 3, and minus 3. So these three are not uh, orthogonal to each other. Like uh, like these two vectors are orthogonal. They have 90 degrees angle between them, or like let's say these two are orthogonal. So these two are not orthogonal. Like if you do the dot product, or like if you find out the angle between them, so these two are not orthogonal. And when you do the dot product, their product is not a unit. Their product is not one. So that or like let's say if you find out the length of this vector, then sorry, not the product, but if you find out the length of this vector, length of the vector is nothing but you have to just take, let's say if you have a vector like this x y z, if you want to find out the length of the vector, this is nothing but the length of the line, right, from origin to the point x y z. So you can take, you can do it as x square plus y square plus z square. So this is nothing but, this is called the length of the position vector. So we can also call this as vector norm. So or L2 norm. So we can also call this as L2 norm. Like you can represent it like this. So mod of, let's say mod of some vector, you can represent it. So this this is nothing. This we can call it as length of vector or norm of vector or something. Like we want this norm of each column vector to be one. So there are like a lot of use cases with this kind of, like if my matrix is like this, it will not be used computationally very helpful for me. Like we have seen, if you have an orthonormal matrix, if you have an if your matrix is orthonormal, when let's say you be some matrix, if you want to invert it, you can just take the inverse of it. You can just take the transpose of it. You will get the inverse. Otherwise, doing inverse is a very difficult thing to do in computers, and there are like large number of errors that will come if we go on, like if you want to do inverse of matrix in the computer. So this is a very error prone and also computationally expensive operation. Like if you have very big matrix, it will be very computationally expensive. Like it will take a lot of time uh, and like energy to do the inverse. So, but if you make this matrix somehow uh, orthonormal using any kind of technique, then if you want the inverse of that matrix, you just do the transpose, you will get the inverse. So that's why it is like very helpful. And what we have to do is, let's say this, uh, I will take this as V1, V2, V3. So these are my three vectors. So first vector, whatever I have, I'll take it as uh, or like I want to make it a unit vector, or let's say I want to make it a uh, make the length of the vector as one. Like what I can do, I can make V1 cap is equals to V1 by mod V1. So whatever the vector you have, you just multiply with this. So x, y, z is there. You multiply this with x square plus y square plus z square. So now the length of this vector will be 1. So first vector has become uh, first vector has become normal vector or a unit vector. So now I want to go to the second vector. So I will take the second vector. So I will take the second vector. I want to make sure that the second vector is the orthonormal is orthogonal to the first vector, right? So that is the point of it. Like all three vectors should be orthogonal to each other. So I'll take the projection of the second vector onto the first vector. let's say if we have two vectors like this, uh, let's- we have two vectors like this. So what like you want to make this vector as orthogonal to, let's say you want to make B as orthogonal to A. So what you can do is you can take the projection of B on A. So if you take the projection of B on A, like B, you can like uh, divide it into two components, right? Like uh, x cos theta, like B cos theta and B sin theta. So if you remove the if you remove the this component of projection of B on A, you will get only this vector. So you are just removing the projection of B on A. Now you can make this vector. Let's say we call it as some B uh, uh, B BB, or let's say BB. So now you can see that after removal of this projection of B and A, this is perpendicular or orthogonal to A. So that is what we will do here. So we will take, sorry, this, we will, now I want to make this, let's say, V2, let's say or let's say I'll write it as O1. So O1, O2, and O3. So O2 I will take. So what I will do, I will take V2 and I will remove the uh, projection of V2 on V1. Okay. So now I am removing the projection of V2 on V1. So you take this is V2, you take 318 and you take 318 into, you after you do this, some value you will get. After you do this, you will get some value, something, you multiply it, you will get some O2. But this O2 will not be, O2 might not be normal. O2 might not be or unit vector. So you can make it a unit vector by taking norm O2 by uh, dividing it by norm of it. So similarly, you can take the third vector. You can take the third vector, which is V3, and you can take the uh, take the projection of that onto the first vector and take the projection of it onto the second vector, and now it will be perpendicular to both the vectors O1 and O2. So both the vectors O1 and O2, and then you will do again O3 divided by norm of O3, you will get O3. So by after doing this all these operations, you will get a vector a matrix, something O1 cap, O2 cap, and O3 cap, and this matrix is called as orthonormal matrix. Okay, because each column vector each column vector is a unit vector, and each of it is perpendicular to each other. Like O1 is perpendicular to O2, O3, O2 is perpendicular to O1 and O2, and O3 is perpendicular to O1 and O2. So that's how we perform this Gram-Schmidt orthonormalization. I am not doing the calculations because like there is some time which we have to manage. So you have, do you have any doubt in this? You can ask me. I will let you know. This is a very like an algorithm like a Gram-Schmidt orthonormalization or orthogonalization is an algorithm which might be helpful uh, in the future discussions which we'll have in the course. Okay. Okay. So then we had then we also have this matrix norms. Like let's say if you have some matrix A is equals to 1, 2, minus 2, 3, 1, 8, and minus 3, minus 4, 3. So now if you want to find out the Frobenius norm of this matrix, so when you have this kind of notation like this, A between this kind of bracket and subscript F, you have this is called this notation is used for the Frobenius norm. So in Frobenius norm, what we do is we just take each element, square it, and sum it. So each element of this matrix is taken, squared, and summed. Like this, we do for all element, and we take the square root. So this uh, is how we do the this is how we can use the Frobenius norm, and like these vector norms, like vector norm, like we have seen that this represent the length of the vector. So matrix norm is also something which we will use, like we might use like lot of time in the future, like this will give some kind of measure of the matrix. So a lot of times you have to like you cannot take a matrix and tell about its characteristic, like how is the matrix uh, so we have to come out with some kind of measures, right? So like for a vector, this is that is the length. Length is the measure of the vector. So for matrix, this Frobenius norm and singular vectors like eigenvalues of a matrix, if you have heard. So those things, those kind of things can be used for a matrix uh, to tell about its characteristics, like how the matrix will behave when we do the inverse. Like let's say if you have a matrix which has an eigenvector eigenvalue as 0, so then it means that matrix cannot be invertible because that is a singular matrix. So that can be told only when you have this kind of numbers, right? Like eigenvalues or eigenvector. So so eigenvalues and eigenvectors can also be like consider some kind of norm, you can say, of a matrix. So spectral norm, what we call here spectral norm is nothing but singular values. Singular values are like you can say same kind of thing as a eigenvalue. Like we will see in the future what are singular values and what are like eigenvalues. So when we go to the structural values part. So Then we went to interpolation. So interpolation is nothing but uh, we have lot of uh, like let's say when you do some kind of measurement, you take like whatever the measurements you take, those are like discrete measurements. Like let's say you are measuring the position of a car moving. So at different times, like the car will have different positions. Obviously, you cannot like measure it continuously because like whatever the instrument which you use, like it will only measure like after a certain interval, like 0 second, 2 second, 3 second, like that. It will like whatever the data which you measure, you will be like that. And if you want to like if you want to if you want to get some kind of information between these 2 points, like at the point at which it is not measured, you can use interpolation. So interpolation is nothing but like reading between the lines. So what you can do is like you can just like if you know the function, it is well and good, but we don't know the function a lot of times, like the function passing through all these points. So we can use some kind of like we can fit some kind of curve passing through all these points, and we can evaluate the value of function at unknown points at which it is not measured. So we can use this like lot of techniques are there. So lot of which we can use. So if you are like evaluating it like in between two known points, then it is interpolation. Like if you are evaluating out of the like measured range, then it is extrapolation. So we can use a lot of different kinds of functions. So this thing will also continue. Like we will solve a lot of problems in the next week also. Like any kind of continuous function, like this is a very important theorem, like which we should know. Like any kind of uh, function which we have, sorry, any kind of continuous function can be on a closed interval, can be uniformly approximated as a polynomial function. So you even if you have a sine function, you can use Taylor series to represent it as a polynomial function. Like you might have heard of Taylor series. Like uh, if you do, if you have not heard, like we will see in the future. So Taylor series expansion, like lot of different things are there. Like any complex function, we can uh, represent it as a polynomial function. So but like what Paul like, but this is not complete. Like this theorem doesn't tell about like uh, what are the constraints which we should have. Like that, like let's say we have this example. Okay, so this this curve is called Range's function. So and this is the function. Okay, 1/1 plus 225 x square. So this curve, let's say you can take some 11 points, 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, and like let's say 11 points you have taken, and you know the value of the function at 11 points. So we know that let's say if you have we know if you have n plus 1 points, using n plus 1 points uh, we can fit a n degree curve passing through the n plus 1 points. Okay, like let's say if you have 3 points, then you can fit a parabola to passing through these points. So this like this. So if you have 11 points, you can fit a 10-degree polynomial to it. But if you take these points uniformly, you can see that you can get the approximation as this curve. But this is like very far from the curve which we want to approximate. So 10-degree polynomial will have a lot of fluctuations like this. It will not give you a correct answer if you fit this curve. But if you fit this curve using the like uniform points of interpolation. Like that's why we go and take some roots of Chebyshev polynomials, like we have seen in the course. Like, and from that we take the points of interpolation. Like, let's say here you take lot of points and here less number of points. So those points you will take and interpolate the function. Then you will get some kind of function which is like okay, uh, good approximator, better than this one, right? Better than this one. So there are lot of things which we have to take care of. So then after interpolation, we have this numerical integration, which also we have to take care. So numerical integration we can use, like as I have said, there is rectangular integration, there is Simpson's rule, and there is trapezoidal rule. So like we can make small rectangles and add the areas of all the rectangles to get the interpolation, to get the uh, value of the limit which we are evaluating. But there is also some kind of technique called Gauss legendary quadrature, which is used in the finite element throughout this course. You will keep on hearing this Gauss legendary quadrature interpolation. So let's see one example. Uh, how we will do it? Like this was in the like this was not in this week, but there were some few questions which were given. Let's say if you have some function like this, -1 to 1, x cube plus 5x minus 4, and x cube plus 3 dx. Okay. So you have a function like this, and you want to integrate this function. So now what we can do is, like, we can use this Gauss quadrature Legendre technique to integrate it. So any integration can be like numerical integration can be like described like this, right? So you will take some I is equals to 1 to, like, let's say how much like if you have, let's say if you are taking n points between, like if you are taking n points and you want to, like, let's say approximate this. Okay, let's approximate this integral. So in Gauss Legendre we will have wi into xi. So here if this interval, if this like, always remember that during Gauss Legendre integration, this integration limits should be -1 plus 1. If the limits are not -1 plus 1, we have to make them -1 plus 1 by using some kind of transformation. Okay. So this is the transformation which you can use, but here it is not required because this is already -1 plus 1. So now I can integrate this function using the Gauss Legendre. Like here they have, like, let's say I'm using 2-point Gauss Legendre, 2-point Gauss Legendre formula to do this. So now I can use this. So in 2-point Gauss Legendre, the weights are 1 and 1, and the sampling points are minus and plus or minus 1 by root 3. So here W1 f of x1 plus W2 x of x2. So W1 is 1, f of x1 is, so whatever this function is there, I have to evaluate it at, this is f of x. Okay. So this is my function. I have to evaluate it at x of uh, what is that, 1 by root -1 by root 3 and f of 1 by root 3. So now if you substitute here in this -1 by root 3 whole cube plus 5 into -1 by root 3 minus 4 -1 by root 3 cube plus 3. Similarly, we can do it for this also. You will get the 2-point Gauss Legendre integration of this function. So you will get value of the integration of this function, which is like very good approximation. Let's say if you have 3 points, like if you want a 3-point approximation, then you can do W1 f of x1, W2 f of x2 plus W3 f of x3. Okay. So here the weights are changes. Okay. So the weights are for the sampling point 0, like there are 3 sampling points, 0, minus root 3 by 5. 3 sampling points which we have are 0, minus root 3 by 5, and 3 by root 5. Root 3 by 5, sorry. So you will take 0 f of 0, and weights are here 1, and weights are 8 by 9 into 5 by 9. So for 0, weights is 8 by 9. Sorry, this is not 0, 8 by 9. And for the remaining 2, this is 5 by 9. So now you evaluate this function at this point and this point, f of root 3 by 5. So if you evaluate it and sum this, you will get the value of 3-point Gauss Legendre approximation of this integration. So that's how we do Gauss Legendre integration. I hope you understood. Any doubts here? Hello, can you hear me? Uh, Sachin or Manoj?
Yes, sir.
It's clear, Anish? Do you have any doubts?
No, sir.
Okay. Okay. So this was like very today we couldn't like there were a lot of things discussed in this week, like related to numerical approximations and all these things. So mostly I couldn't cover. I covered a lot of them, but these things you might think as like not very important, uh, but we should know that these things exist, so that we can use this going forward in the course, and it will be helpful for us. So uh, obviously, like if you have any doubts regarding uh, regarding this course, or like in the future also, like not in, you can ask me in the problem solving session, or you can also mail me here. So you can mail me anytime, like